So good morning or good afternoon or good evening, everybody, depending on where you are. So my name is Jin Kim, and I'm an assistant professor at the University of Alabama. And it is my great pleasure to be serving as the host for this session today. So as you can see, we have a great talk by Beomjin Kwon. And please wait until the end of the talk as well, because Vladimir will also briefly talk about the Gordon conference that's coming up in January. So then with that, let me quickly introduce our speaker for today. So Dr. Beomjin Kwon is an assistant professor of School of Engineering of Matter, Transport, and Energy at Arizona State University. So Dr. Kwon received his PhD in mechanical engineering from the University of Illinois at Urbana-Champaign in 2013 under Bill King and 𝗧𝗿𝗶𝘁𝗀𝗃. And then he worked as a senior research scientist at Korea Institute of Science and Technology. And then she came back to the postdoc at UIUC again. So Dr. Kwon's overarching research goal is to radically improve the thermal and fluidic systems by leveraging the data-driven design and additive manufacturing. And his research has been sponsored by various organizations, and he has published more than 40 peer-reviewed papers. So without further ado, let's welcome today's speaker and hear his story. Thank you so much.
Right. Yeah, thank you for the nice introduction. So yeah, I'm Beomjin Kwon from Arizona State University. It's my great pleasure to speak in front of such many professors. Actually, I think it has been a while since I talked in front of many professors since my defense exam. And so today I'm going to talk about the opportunities in heat transfer systems, 3D printing, and machine learning. So basically, I'd like to share my ideas about how effective, how useful the 3D printing and machine learning are for modeling and designing of heat transfer systems. Right. Okay, so before I get started, let me briefly introduce Arizona State University, ASU. So our school is a public school located in Phoenix, and ASU is one of the largest public schools in terms of the enrollment. So back in 2021, we had about 135,000 students and 58,000 online students. So our school is as big as a small city, right? So we have actually more than 400 undergraduate programs and majors. It's a quite big school in terms of the size. And so if you have a chance to visit our school, you're going to see many enthusiastic students and also tall and beautiful palm trees on the road. Right? So please visit ASU if you have any chance. All right, so as a start, so let me introduce my research goal. So my goal is basically to discover effective designs of energy systems using advanced methods and knowledge. So basically, I'm a person who likes to study heat transfer physics, especially focusing on flow, heat, structure interactions, and material morphology dependent heat transfer, right? And also, I'm a person like to use additive manufacturing to make many complex 3D structures. So in my laboratory, I have a 3D printer, and my students use that to fabricate, optimize, and customize heat transfer systems. And in order to model complex thermofluid sciences, I recently started to use data science methods such as deep neural networks. So basically, I use the neural networks to express complex correlations, including numerous variables. And sometimes I generate interesting, innovative designs using machine learning methods. And lastly, my goal is to optimize the structures of heat transfer systems while considering the design freedom of 3D printing and by using the power of data science. So with these four basic elements, my goal is to make impacts on the following applications, such as heat exchangers, heat sinks, thermoelectric generators, and composite materials for energy transport. All right, so, and first of all, let me talk about the challenges in our traditional design processes for heat transfer systems. So when we try to come up with the designs, actually we typically consider a couple of factors, including physics, performances, manufacturing, and related costs, right? And actually we employ a couple of methods. Traditionally, we typically adopt the designs that we already validated by our experience, or sometimes we derive the design from our intuition, numerical simulation, or simplified equations. And we also consider the design constraints, and I think the major design constraint is manufacturing. So we need to think about which manufacturing tools we can access, and we also consider how long it takes, how much it costs when we make the systems. So with these methods and consideration design constraints, we have been proposing some useful designs for many thermal applications. But the question is how efficient, how optimal those designs are. And is there any way we can improve like this existing approach? Okay. So I had this question over a long time, that the question was, so can we exploit the recent advances in technologies, right? So to answer this question, I thought about many approaches, and currently I'm trying to follow this strategy. So maybe we can develop new design methods using AI or algorithms, because in many different fields, people already use AI or algorithms to generate non-conventional innovative designs. And maybe we can employ deep learning model to rapidly and roughly approximate the performances of newly generated design. So we can basically filter out some not relevant, not good designs using this deep learning model. And maybe we shouldn't be too restricted by manufacturing anymore by exploiting the design freedom of 3D printing. So nowadays, there is a growing interest in 3D printing because we can make many complicated structures without much cost and without much complexity in manufacturing. So my basic research direction is to employ the machine learning and 3D printing to improve our design process for heat transfer systems. And I'm going to talk about my recent endeavor along this direction. So the first part is the design innovation enabled by 3D printing. So with the additive manufacturing, we can print various materials, including metals, ceramics, polymers, and so on. And I have been seeking the opportunities, particularly from polymer AM, because of its unique benefits. So with the polymer AM, you can make things much cheaper than metal 3D printing. Sometimes it can be cheaper more than 10 times. And with the current polymer 3D printing techniques, you can make things with the micrometer resolution, okay? And when you employ a transparent regime, you can make transparent devices. So those are really useful to visualize the flow and even temperature inside your system. And the 3D printed polymer actually contain relatively high density, so fluid leaking is not a big issue. So this picture shows the 3D printer in my laboratory. So I used stereolithography 3D printer. And with this printer, my students were able to make many interesting thermofluidic structures. And we do lots of experiments. And the first, actually, the project I like to introduce is the innovation of a cold plate integrated with steady mixers using 3D printer. So just to briefly introduce the cold plate. So here I show a common metal cold plate, which includes metal tube inside. So inside the tube, we generate coolant flow, and this coolant can absorb heat from certain heated surface or hotspot, right? And so that's actually the basic idea of cold plate. And in order to improve heat transfer, sometimes people try to integrate a steady mixer, which sometimes we call as turbulator. And also, let me introduce briefly about this. So, when there's a coolant flow over the heated surface, what usually happens is hot fluid is confined within very thin boundary layer. However, the majority of cold fluids simply pass through the tube or pass through the channel without participating in heat transfer. So what people do is integrate steady mixer, something like this, and then we can rotate the flow, mix hot and cold fluids, and you can utilize more amount of fluid for absorbing heat from the heated surface. And then people were able to enhance heat transfer more than 100% or more. Then what is the problem, actually? Actually, there has been a problem in manufacturing of steady mixers. So the state-of-the-art technology in the industry is surprisingly still simply twisting metal film to make the steady mixers, or we inject plastic inside the mold and then create such twisted steady mixers. However, of course, the challenges are, so with this manufacturing techniques, it's very difficult to optimize the structures of static mixers for various applications. And also the state-of-the-art technology to install these mixers inside cold plate is simply manually bring your mixer inside the tube or channel and use the glue to stick them on the surface. So there has been some challenges in using steady mixers. So we were trying to tackle this challenge using polymer 3D printing, and the technique we used was continuous liquid interface production. So in this picture, I show one cold plate integrated with steady mixers that we 3D printed. So using a single 3D printer, you can actually easily optimize all the dimensions of the steady mixers and cold plates, and you can simply integrate the mixers without additional installation process. So the major benefit of 3D printing is that we can easily optimize the structures for each application. And so we were trying to optimize the mixer designs through numerical simulation. So in this work, we numerically simulated two different types of steady mixers. One was the twisted tape mixer having corkscrew shape. So that's a traditional type of mixer. And we optimized the twist ratio and other relevant sizes for our heat load and flow condition. And also we proposed a new design, which is called as chevron mixer. Actually, it has twisted parallelogram, but in this picture, actually, it looks like a triangle. But what it does is it scoops up the hot fluid from bottom of the channel to the top side of the channel and slightly rotates the flow. So compared to the twisted tape, the chevron mixer actually blocks less cross-sectional area of the channel. So this mixer is supposed to offer less pressure drop than the twisted tape mixer. So again, so through the numerical simulations, we optimized the sizes and shapes of the devices. And by using a single 3D printer, we were able to make many different prototypes, but here I show only two cold plates. So these photos show the top view and front views of the steady mixer inside the cold plate. So from these photos, now you can see that the chevron mixers have twisted parallelogram shape. And because we wanted to use this for heated surface, we employ a high temperature polymer, which can withstand above 200 degrees C. So this place can be used for some mild cooling applications. Right. So of course, we tested the performance of the optimized cold plate, and here I show the experimental results showing the convection heat transfer coefficient versus the water flow Reynolds number. And the dashed line and solid line here represent the data from plane channel without any steady mixers. And here I show the data from the channels, including steady mixers. So we were able to increase the convection coefficient more than twice. And we also estimated the increase of convection coefficient per increase of pressure drop, and it was greater than 1 for the twisted tape. But for the chevron tape mixer, the pressure drop was less, but the improvement was a little bit slightly less than that those for the twisted tape. So it was almost close to 1 for the chevron mixer. So I think this example demonstrates the usefulness of 3D printing for the cold plate. And in another project, we also use 3D printing to innovate the design of jet cooler. So the jet cooling actually is a technique to create high-speed fluid flow and achieve extremely large convection heat transfer coefficient. So for example, if the Coulomb flow's Reynolds number is on the order of 10,000, you can also achieve the convection coefficient on the order of 10,000, which is about 100 times better than what you can achieve using slow fluid flow. Right? So because of that, jet cooling is considered as very powerful cooling approach. However, if you want to make very compact jet cooler for electronic system, it's actually very challenging if you're trying to combine top-of-the-shelf fluidic components. So to tackle this challenge, we also employed 3D printer to realize compact jet cooler for small electronics. So these pictures show the jet coolers we created for a small PCB, including working transistors. So these transistors generate heat, and we try to cool down these transistors so that we can supply more power and operate these devices with more power ratings. So what we did was optimize the flow passage of the jet nozzle. So we gradually shrink the flow passage from the original flow supply to the final nozzle exit, so which reduces the pressure drop due to abrupt change of flow passages. And also we optimize the nozzle diameter and the spacing between the device to the nozzle exit. So all those, the parameters are very critical in the jet cooling performance. So we optimize those parameters, and then so through this numerical simulation, and then we were able to 3D print this system. So I want to show a video that demonstrates the performance of our jet cooler. So this image was taken by infrared camera. And then when you operate the transistors, now the temperature increases up to actually slightly above 90 degrees C. And then when you inject air jet, the temperature almost instantly drops to room temperature. But as you stop the jet flow, then temperature increases again. But if you inject the air jet, again, the temperature drops to the room temperature almost instantly. So and I also want to comment on the advantage of 3D printing here. So in reality, there are many different types of electronics, right? And in those electronics, hotspots are located at different locations from device to device. Then how do we deal with all those different electronics? So we cannot mass manufacture jet coolers for all those different electronics. However, if you have a single 3D printer, or if you just have just a couple of 3D printers, actually we can deal with all those many different electronic layouts, and we can also try many different cooling configurations. So for example, if you want to cool this hotspot by injecting flow from top and bottom side, what you can do is simply alter your jet cooler design and then simply print it, right? And also, if you want to cool down the hotspots located on top and bottom, you can also change the jet cooler design, something like this. And if you have many different electronics, or if you want to cool them down with different approach, it doesn't take much time. It doesn't take too much cost for for altering the designs and making the jet cooler. So I think the economy makes sense if you try to use if you want to deal with very small amount of electronics where you cannot really mass manufacture your cooling solution. So in the next part, I'd like to introduce my recent work using machine learning. I think currently there is a growing interest in using machine learning because in order to overcome the limitations in our modeling and designing of heat transfer systems. So since mid-1990s, machine learning already has been used for thermophyletic research. And at this early stage, people employed neural networks to fit very complex experimental data, including many variables, and for the data with nonlinear trends that simple mathematical equations cannot be easily used to fit those data. So here I show one example. So when you use mathematical formula to fit the experimental data, sometimes you get very poor accuracy. Actually, that's true for many thermophyletic phenomena. For example, our correlations for turbulent flow, actually, the accuracy is, I think it's less than 90%. So, but however, people found that when you employ neural networks, even for the complex experimental data, you can fit with much greater efficiency than the mathematical formulation, right? So people already have seen the potential of machine learning, and recently, due to the advances in computers and the machine learning algorithms, now people are trying to apply machine learning for more advanced tasks, such as approximating transient dynamic field information in thermophyletic phenomena. So, so people were able to approximate the velocity, pressure, and streamline variation over time in dynamic systems. So due to the increase of interest on machine learning, we also try to employ a deepfake technique for approximating the heat transfer problem solution. So first of all, what is the deepfake? So this is the ability of AI to fabricate apparently real footage of people. So I think many people already have seen the news articles that the deepfake program can generate the fake images of Einstein, Mona Lisa, and also even your faces with various facial expressions. And deepfakes use several artificial neural networks, such as generative adversarial network or autoencoder. Then I had a question that can we use deepfake to make images representing the heat transfer problem solution, okay? And in many heat transfer problems, actually, we can express the input and output information using images. So here I show one simple example. So in this image, you can express the channel geometry and the temperature in fluid and wall domain, right? And we can also express the temperature distribution in your domain, and also you can embed lots of heat transfer properties inside the image. So maybe if you train a deep neural network well, maybe we can convert this input image into the corresponding output image. So with this hypothesis, we try to train a deepfake method for a simple heat transfer problem. So, so we use a deepfake technique for solving a very simple 2D steady-state convection problem. So in this problem, the input image shows the initial conditions, and that consists of 3 channels similar to the regular RGB images. And in the first channel, the pixel values represent the Reynolds number distribution. And in the second channel, the pixel values show the Prandtl number distribution. And the third channel was for the initial temperature of the system. And then the output image shows the steady state solutions. And so in the first channel, it shows the friction factor distribution. In the second channel, it shows the Nusselt number. And the third channel was for the temperature distribution. So, and so by combining the first, second, and third channel values, actually you can create the input and output images. And as a deepfake model, we employed conditional generative adversarial network. We often abbreviate it as condition again. And we supplied the input image into a deep neural network called generator. And what this network does is convert this input image into the corresponding solution, which we call as fake image. And in order to train this generator, we need another, the second neural network, which we call as discriminator. And what this network does is actually compare the solution of the problem with the fake image. And the solution actually comes from numerical simulation. So we need to prepare some training data obtained from numerical simulation in order to train your model. So, so the discriminator actually catches the difference between the fake image and the ground truth data, and then provide feedback to the generator. So through this way, you can train the generator, and then we were able to predict the solution for this simple problem. So the trained generator was able to infer the temperature, Nusselt number, and friction factor distribution simultaneously within seconds with less than 3% error, especially for the channels having similar geometry to training examples. And the error increased to 12% for the channels having modified geometry. So here I show a very simple example. So there's a water flow in the middle, which is surrounded by heated wall outside. And the generator network was able to predict the temperature distribution, which is very close to the numerical simulation. And at the same time, it also predicts the Nusselt number and friction factor distribution, which is shown on the right side plot. And this single model can predict for laminar flow, transitional flow, and even for turbulent flow very accurately. And then we also tested the model using somewhat modified channel geometry. So for example, here we supplied a 90-degree rotated channel, but still the generator network was able to predict temperature distribution, something like this. And then we thought that maybe making the input in the image format takes lots of effort for the users. So we developed a second generator, which simply uses numerical vector as input. And the numerical vector actually includes the aspect ratio of channel, Reynolds number of the flow, and other relevant information. So user can simply put all this information just in the format of vector, and then if you supply this to generator network, now what it does is it upscale this information and then produce the corresponding temperature data. So we tested this vector to image generator network for a mixed convection process. So as you know, mixed convection is very transient and highly nonlinear process, which is very difficult to express, predict with using mathematical formulations. And the mixed convection actually combines natural convection and forced convection and generate uprising, circulating flow motion and also heat flow. So here I show some example of the results. And so if you input the time and location of the channel, then the trained generator network can predict the temperature distribution across the cross section of the channel, and which were very close to the simulation data. And now you see the videos created by our generator network. So we actually, so this video shows, this animation shows the temperature variation at a certain position inside the channel. And then we study the morphology-heat interaction in composite materials using deep learning. So especially we studied the thermal and electrical conductivities in copper carbon nanotube or CNT composite materials, because copper CNT composites are considered as promising conductors. So there has been like significant interest in CNT materials over a long time, but as you know, so these materials have not yet successfully commercialized for many applications, and the major reasons are actually the CNT composites involve large interfacial resistances between CNTs and the matrix, and also it's really difficult to homogeneously disperse CNTs in the matrix. So when you design your composite materials, it's really important to understand the effects of interfacial resistances and the dispersion, how you distribute the CNTs in the matrix. And the problem is, if you try to simulate the CNT composites using numerical simulation, it takes a very long time due to the extremely high aspect ratio of CNTs. So we try to tackle this challenge using a deep learning technique. And in this method, we employ the composite materials morphologic images as input. So basically, we randomly generated the morphologic images of copper CNT composites having different fractions. So here, the black horizontal lines correspond to the CNTs. So we randomly distributed, and then for the target fraction, and then we actually fed this image into a convolutional neural network. And when this input image passes through multiple convolution layers, the data contained in this image actually gradually shrink. And then at the end of this neural network, the information eventually converted to the electrical and thermal conductivities simultaneously. So these two plots show the electrical and thermal conductivities predicted by our simulation model and the convolutional neural network. So as you can see, the predictions between these two models compare fairly well without much error. And then for various interfacial resistances and for various random distribution of CNTs. And actually preparing the training data took quite a long time because for the simulation, it took more than 100 minutes for a single morphological image. So if you predict the electrical and thermal conductivity for this single image, especially with the high fraction image, it took more than 100 minutes, I think. So my students took I think several days, not just several weeks actually, to prepare all the training data. But the trains in a convolutional neural network, it takes less than 1 second to predict for one image. So even though you change the distribution of CNTs, if you change the size of the domain, still our model can predict for those images within less than a second. So I thought that those were pretty interesting demonstration of using deep learning for some fundamental thermofluidic problems. So in summary, so I have been so my research group has been working on how to use 3D printing to explore more efficient designs of the cold plate, jet coolers, and thermoelectric generators. And we also explored the machine learning and deep learning techniques to rapidly approximate the solutions of heat transfer problems. And I think I see huge opportunities in 3D printing and machine learning. And I think our community can work together for this direction, and then we can make huge impact and innovate the designs of future heat transfer systems. But of course, our community, I think, have a lot of questions about some limitation in this technique. So I think if we can actually collaborate and work together to resolve those challenges, I think we can see some bright future from the collaboration. So I'd like to thank to the organizers of the Thermal Transport Cafe to share my idea today. And I also like to thank my PhD students, my collaborators at University of Illinois, UNIST, and my sponsors from NSF, JPL, and Korea Institute of Science and Technology. So with that, I conclude my talk today. And yeah, please let me share your questions and let's discuss. Thank you.
Okay, thank you very much, Dr. Kwon, for a great talk. And if the attendees could show, I don't know, clapping hands or something like just Daniel did, go ahead and do that. And so then I think we have time for a couple of questions. So feel free to unmute yourself and go, or just raise your hand or put that in the chat box, depending on your preferences. So I see Danny Oraham.
Morning, guys. How are you?
Hi.
Thank you, Beomjin, for the very nice and interesting talk, actually. So I am more in the experimental side, so I'm going to ask you maybe for the first part a little bit of your talk. I'm very interested also on the versatility and capabilities of 3D printers as well, right? You didn't give us many details, though. Can I ask you, so I think you are using this polymer that withstand kind of 200, 220 degrees or so. Right. Can I ask you about the resolution in terms of spatial resolution of the features that you can make with the 3D printer, versatility of materials? To this end, also, you are using polymers that sometimes they are not really conductive, and for heat transfer, we want them conductive. Do you have any insights here on 3D printing of ceramics, for example?
All right. Yeah, I think that's.
Let me know your thoughts. I ask you many questions. We can have a back and forth discussion.
Yes.
Very interesting.
I will need your help to, so remembering some questions. Yes, I think that's your question actually. The major questions in the field. So first of all, so currently, the polymer 3D printing actually provides very high accurate resolution. So even my printer in the lab, it can print. It's actually pixel size of the printer is 25 micrometer. So we can easily make like 100 micrometer features using this printer. So the resolution is quite high. So this actually shows that a jet nozzle having, actually there are many jet nozzles here. And one of the smallest nozzle has the diameter of 100 micron. And so it's very easy to make using polymer 3D printing. But so currently using metal 3D printing and ceramic metal printing, the resolution is, as far as I understand, is limited to so a few millimeters if you want to make such a big system. But there are like 2 photon, 3D printing, very advanced technique. But you can, and with that technique, you can make very small size device. But the cost of the printer is just a couple of $100, dollars. So that's way too expensive right now. And the material, of course, I think it's very important for many applications. So for many like heat transfer system, of course, we want like thermally conductive material when you want to directly contact on the hot spot. But in my research, I explored actually non-contact type, non-direct contact type, heat transfer solution. So for the cold plate, actually the coolant directly contacts the hot surface, so the polymer didn't directly contact. And for the jet cooler, again, I'm only shooting the coolant into the hot spot, so polymer doesn't really directly contact the heated surface. So for this type of application, I think there's no, so we can still use polymer AM, but of course, if you are interested in making direct contact cooling solution, and if your coolant should go way high, like high temperature, and of course you want to employ metal 3D printing, and sometimes but the problem is that the variety of materials for 3D printing is still quite limited. So that's why there are many still funding opportunities developing novel 3D printing materials. And there are many like material scientists, working on that field, and so that So I think so developing 3D printing process for novel novel materials with high conductivity definitely very important for our future direction. And so I'm trying to collaborate with the material scientists who actually print highly conductive material. So then if I can, make the result with them, maybe I can, show you some interesting result with the high conductive material next time.
Yeah, and also I'm going to add with that one with the metal 3D printing. So we are able to print like roughly 400 micron features, 𝗙𝗫 for inconel, GR copper for the rocket engines. So metal can go very high, powder bed fusion.
Thank you very much, Beomjin. I think you have answered all my questions, actually. Just one very small thing. What is the actual roughness of these structures?
So as I said, so the roughness actually what we measured was around I think 100 or 200 microns. Yeah. Right. So our pixel size is 25 micrometer. Mm-hmm. But still, so the feature we make does not exactly have 25 micrometer, because it's simply solidify 25. Try to solidify 25 micron, but the UV light actually disperse slightly neighboring region, and it creates some roughness features, and we try to measure that using microscopes in the lab, and we observed that those are few hundred, maybe about 100 micrometer, but considering the size of the channel and size of the nozzle size here, the roughness effect was not so huge, but sometimes people try to take advantage of the roughness created from the 3D printing. because it also generates some, so flow mixing motion locally, and that can actually help you to increase heat transfer as well. So
excellent, thanks a lot.
Yeah, thank you.
Matteo, please go ahead. Please.
Beomjin, I actually have a follow-up question related to materials. So I was wondering if you have any experience using these plastics with refrigerants or dielectric fluids.
Oh, not yet. So far I have been testing these devices only with water flow and air so far. But of course, dielectric coolants should be very interesting. And actually, I'm actually submitting proposals with many interesting dielectric coolants, but yeah. So that's one of of course that's actually a very good I think future direction.
Yeah.
So you go ahead.
Yeah, actually, the question I had, and sorry, Vladimir, I'll leave you at the floor soon, is when you think about reconnecting these two areas, where you presented two topics today, which are 3D printing and somehow some machine learning, right?
That's right.
I was curious to pick your brain on how do you foresee to develop research interactions between the two. So what kind of practical application do you have in mind, and how does it practically work?
Right. So actually I'm trying to so my long future goal is to combine 3D printing and machine learning to introduce some innovative heat transfer system design. So when you use 3D printing to create some interesting things, so actually how do people design? So again, so even though you have 3D printer, what people still do is use their intuition. So maybe this complex shape, so because we already studied heat transfer physics, we can actually think about some creative designs from our intuition, and then we propose. That's actually almost most of the researchers do right now. But I want to simply overcome that approach. Maybe we can use AI or algorithm or deep learning model to explore more complex three-dimensional design space. And then so after optimizing the design using this deep learning approach, then we use the design to 3D print and then experimentally test. So right now I do a project with JPL. We are trying to make very compact, effective heat exchangers for JPL mission. So they want to reduce the weight, but of course achieve very high heat transfer coefficient. So we submitted a paper about optimizing the shape of the fins inside the heat exchanger using machine learning, and then we are going to test after we 3D print those systems. So yeah, I think you're going to see the papers maybe this year and next year with this, and of course I want to advance this approach for more complex problems.
And just quickly, Matteo, I wanted to tell you that, so for my PhD project, I 3D printed the chevron type, the plate heat exchanger with the 3D printed, the polymer, and it worked. So just wanted to add that.
One of the things also you can think about, probably you can, the merging of the two of your concepts, even the 3D printing itself, the process is not optimized. So you can use your machine learning to optimize your printing process also. A lot of parameters are unknown. So you can use that approach also.
That's so true. Yeah, that's so true. I think I see many, yeah, I think a lot of people also want to go to that direction when I talk with the material scientists. So yeah, I think there's a huge opportunity for that.
Yep.
Okay. So then, I guess next, Vladimir, if I didn't mixed up the order.
Okay, thank you. So for the cooling by air jets, what kind of design optimization did you do? Because I would imagine that the key things there would be kind of the flow rate of air and the timing of this, which could probably be done with some feedback control, but not so much the design of the nozzle. Am I not understanding that right? Or
oh yeah, actually I didn't really elaborate how we optimize. So basically, actually we simply consider a steady state operation, not transient operation. So we so I found that for jet cooling, the spacing between the nozzle exit and the heated surface is quite critical, and also the length of the nozzle. So the length of the nozzle actually determines the flow state. So you must have sufficiently long length in order to achieve fully developed turbulent flow. And also if the spacing is too small between the heated device against the heated device, then the jet on the surface jet actually interacts with the nozzle flow, the flow at the nozzle. So if you bring your nozzle extremely close to the heated surface, actually it makes the heat transfer worse. But if you also put the nozzle too far away from the heated surface, actually your air jet actually spreads out and the flow speed is too slow on the surface. So basically we optimize the basic the heat transfer parameters related to jet cooling, and also we apply topology optimization in order to minimize the volume. So there's a topology optimization tool that minimizes that can help us to minimize the weight and volume of the whole system. So we went through the topology optimization in order to use the least amount of material for and to achieve the same amount of heat transfer the performance. So those were the objective we did. But as you said, yeah. So you can optimize for various objectives, and if you consider some transient operation, and if you consider like some different goal, of course, I think you can actually make you can come up with different designs than this. That's so true. Yeah, your comment is so true.
Yeah, because it would be, I imagine that those kind of hot spots, they may appear certain times, and then they may be not as much heat generation at other times. So if it could be some feedback control for these types of systems, that would be interesting.
That's right. That's right. So we also thought about having some valve inside the tube, and so that maybe we can. So if one transistor is working and the other one is not working, maybe we can close the nozzle and then bring more airflow onto the second nozzle, and then we thought about the switches, including valves into this system, and maybe they can help to deal with the transient operation. But maybe there can be much more better ideas, of course. Yeah.
Thank you. Very nice talk. Thanks.
Okay, then next, Gerhard, I guess you can go, and maybe this can be the last question if we don't have anything quick after him.
Just one suggestion, maybe to work with the 3D printing of composite materials to take advantage of high conductivity and the usual way to produce this kind of heat exchanger. Thank you for your really interesting topic.
Right. So yeah, actually, I'm actually at the design side of the 3D printing. So I haven't actually, unfortunately, I haven't had a chance to mix some different materials to make composite materials to do the 3D printing. But yeah, but you're right. I mean, there's a huge opportunity employing like novel composite materials for their heat transfer applications, and but currently, I'm just on the design side of the composite materials and 3D printing. I mean, the 3D printed heat transfer systems. So yeah, I think maybe some other speakers in this series, or maybe some other people can give you better answers for that. But but definitely I agree. The novel composite materials are definitely needed for the future applications.